Hello. Okay, good, good. Thank you, Frank. Thank you for your wonderful introduction. And good afternoon, everyone. Thank you so much for being here. My name is Jin Chi Young, and I think that before we launch to the scientific part, I would like to thank the committee, actually my colleagues, for inviting me to present our recent study. So the talk title today will be toward low-dimension complex oxide and the twisted oxide neo-architectures. So I think to begin with, I would like to start with some introduction about what we are capable of. So basically, we focus over the past year, we focus a lot based on those kind of complex oxide. Basically, it's an important branch of strongly correlated systems. Okay, so to have those kinds, or to be named as complex oxides, so basically you need to have multiple elements. So of course, oxygen is one of them. Okay, so when you have more than 3 atoms combined together and they can talk to each other, we will call this strongly correlated system or the complex oxide. Okay, so in complex oxide system, they are actually, you can find a wide range of the functionalities. So for example, you can have a classic high temperature superconductor, you can have ferroelectric, CMR material, multiferric, and so on. So basically, every single material you see on this table, it can be easily ground in my lab. Okay, so over the past few years, when it traces back to 2019, we wrap up the growth feature for the complex oxide. So basically, you can try to use different kind of approach and to make the materials into different form. So for example, we will have the epitaxial, for example, bilayer or super lattice. And of course, you can pick up different material and try to fulfill the so-called spin-nodal decomposition, which is studied in thermodynamics. And you can make them into nanostructures. Okay, and of course you can use some spatial tools and to make them into the nanocrystal form. Okay, so this is not what we are going to talk about today. So if you have interest, you can refer to some previous paper that we published. So now, looking at this old roadmap, we start to ask ourselves a question, whether there's a different field that can be initialized by our lab. So what comes to our mind is the freestanding matters. Okay, so you start to think about over the past 15 years, and basically low-dimensional physics start to emerge and come to the daily life, right? So basically, we start to ask ourselves whether we can create those kind of freestanding complex oxide system. But if you have been to senior high school, you will know that in the complex oxide system, because they all have those kind of oxygen atom. So they will basically form, they are basically formed by those kind of ionic bonding, so which is very, very hard to be broken to make them into freestanding form compared with those van der Waals bonded system, right? So we start to seek for some solution. Luckily, if you look back to like 25 years ago, so there is a process in semiconductor which is called laser tip-off or laser leap-off. And basically, you make the epitaxial structure, and you have the laser, and basically you bombard or break the interface, okay? So that you can get the freestanding matters. However, during a period, the damage to the surface or to the interface is too severe. So basically, you can only get micrometer thick fin. So very, very hard to make them into thin fins. So luckily, back to 2016, a team, Ramesh's team in Berkeley, what they essentially found is that you can make them epitaxial growth, okay? But in between, we will need a sacrificial layer, which is also epitaxial materials as well, okay? So in Ramesh's team, what they found is that a classic CMR material, which is called lanthanum strontium manganite, LSMO. So what they found is that you finish the structure and you make the LSO in between the materials and you put it into AC solution. So you wait for a couple of days. So this is something you can have, all right? So you might wonder that whether it is possible to do it in neutron solution, simply because if you merge your material in AC solution, sometimes it will do some damage. Okay, so in the same year, a team in Stanford, which is Hannah Huang's group, what they basically found is the strontium aluminate. This is a new material, and basically it can easily dissolve in water. So that means you use the same thing, you make the epitaxial materials, and you merge that into the water, and basically after probably 2 weeks or 1 week, then you can have the freestanding form. So it also tells me that the current approach to get a freestanding oxide are basically some limited. They are basically limitations. So we start to ask ourselves, we need whether we can develop a new material which we can enable us to get faster freestanding thin film, so to get it fast, okay? To get it, the whole process done as soon as possible, okay? So then we come back to, we occasionally find a classic material, which is the classic superconductor, high temperature superconductor, YBCO. So we occasionally found that this material can be easily dissolved in water or a very, very light acid. So compared with LSMO, you see this is the previous sacrificial layer proposed in Berkeley's group. Usually it can be easily aged. But this time, what we essentially do is that we have the YBCO as the sacrificial layer, and on top we go LSMO. Okay, so you dip them into the very, very light acid solution, and after probably like 10 seconds or 20 seconds, so this is something you can see. Okay, so you will see the epitaxial substrate as a single crystal substrate just drop at the bottom. Then on the surface, there is a floating freestanding thin film. Okay, so this is what exactly we can do. So unfortunately, Paul Ju is not here. Well, I think that he would be a bit, I hope that he wouldn't be mad at me simply because I just used the classic YBCO as the sacrificial layer. But anyway, so this is the classic X-ray diffraction that we can have. So basically, this is the ground sample just prepared by once we get it out from the chamber. So we'll have a single crystal, then we'll have the sacrificial layer, and we'll have LSMO. This is a target material. But after freestanding, we'll do the X-ray diffraction for this layer, and basically what you see is whatever you want, and then you put on top of the YBCO. Okay, so you can do this kind of high resolution TEM or the reciprocal space mapping and try to reveal whether the structure is intact. And please try to be convinced that the structure is perfectly maintained after freestanding. Then we started to do some trivial study. For example, we started to cut down the thickness of a freestanding layer. Okay, so for example, what we found in Strongson Titan is the classic quantum ferroelectric materials. When you try to cut down the thickness of the freestanding matter, so you will see it has a phase transition from cubic, P4 mm cubic, into a tetragonal-like system. So in which you can find some delocalized electrons behaviors. So if you have interest, you can refer to this paper. But also, to get it a little bit further, we also help my colleagues in Swiss Light Source. We help them to develop a new tychography-based or synchrotron-based techniques. So by which, what they can essentially do is that they can use the tychography-based, the synchrotron X-ray absorption spectroscopy. They can simultaneously resolve the anti-ferromagnetic cycloidals and the ferroelectric domains. Okay, so it just got published last month. But today we try to go a little bit further, just try to beyond low-dimensional complex oxides. But before we head to the twisted data structures, I would like to mention that back when we tried to do very back of the 2019, when we successfully developed the freestanding approach for complex oxide, and basically we can also compose the same thing look like the Murray studies in, for example, bilayer graphene or bilayer TMDCs. Okay, so over the past year, we have paid a lot of attention, and recently we get some good result, but through the assistance from my colleague, Professor Chen Chen in Beijing Tsinghua University. What they can essentially do is together we have developed the 3D, or they also want to call it 4D, which is a layer resolved TEM. So basically you can see that this is a layer rotate. If you look through layer by layer, so you can start the mirrorate what happened just right at the interface, and just if you go beneath that, then you will go back to the original areas as well. So you can also find the different tilting structures in the materials, which is pretty exciting. But currently the work is under review in some way, and so that I hope that pretty soon we will have the chance to come back to keep you posted. So let me try to get you back to the main, I'll say, roadmap today. So basically, as I mentioned, in addition to the traditional architectures that we can also have low-dimensional complex oxide system, right? So let me try to get your attention back to the epitaxial growth point of view, okay? So if you have ever tried to do some single crystal epitaxy or growth, and basically you can see this is a traditional, I would say, schematic. So this is the single crystal substrate, right? So you have the regulated patent over there. Basically, they are the lattice. Okay, when we put